Good day everyone, my name is Tim Low and together with Dong Chen we would like to present this paper called the Condensation Analysis Extension to NatHERS or Nationwide House Energy Rating Scheme software. The background for this was that in 2019 for the first time condensation management was introduced into the Australian National Construction Code. Together with this was also the provision for a verification method involving the modelling of a particular way of construction. The idea of modeling was also brought up a few years earlier in the standard, the AS 4200 standard on pliable building membranes, where it was recommended that for certain constructions, especially in cool climates and places where there was a concern for bushfire resistance, condensation risk analysis using ISO 13788 would be appropriate. ISO 13788 is a standard that looks at vapor diffusion using a method called the Glaser method, and it is done on a monthly basis. Now, there are a few software that you might be already familiar with. One of them is Woofy, that marks the specialist end of condensation risk analysis, and also a more basic one called JPA Designer. We felt something like that, like JPA Designer, might be actually more appropriate to the Australian market, which was coming into condensation analysis for the first time. We have had energy efficiency introduced sometime in 2003, and this was mandatory for houses from that point onwards. And we can see that the take-up rate using NatHERS software is actually very high, especially in cooler climates. So if I zoom in at places like Tasmania and Victoria, the southern states in Australia, we find that the take-up rate is almost 100% if we were to compare the number of NatHERS certificates against the building approvals for the same months. Now, Chinoth engine is the engine that underpins NatHERS, and the name Chinoth comes from a couple of terms. One is Cheetah, which was a software just prior to NatHERS, and NatHERS itself. So based on the same kind of etymology, we thought that an appropriate name exploiting the Safari team would be Hyenoth, being a high growth thermal extension to Chinoth. Now, Chinoth has two modeling inputs. One is the building model itself, and the other is the weather file. This too would go into the engine, from which you would get a star rating to see whether it was compliant with the requirements of the code. And another was which was be very useful for further analysis, was the temperature profile. What we were thinking is that we could take the temperature profile, put that through the ISO 13788 method and come up with a condensation profile. And to make this actually even more representative of a real world example, we were thinking that we could also replace the weather file that was included in the database with the weather file that we were downloading from the Bureau of Meteorology. The idea behind High Enough is that it was going to be a software that's going to be open source so that other building scientists who have an interest in this could take a look under the hood, see how the snippets are written, and make their own amendments or recommendations. Why do we want to have weather files that are real world rather than synthesized? Here's an example. We're looking at the weather file for Hobart, which is the southernmost capital city. The gray color shows you what is on the embedded database. The gray, so we find that the box plots generally are much closer to a comfort point of say 20 degrees Celsius compared to the BOM files, which are both wider in spread and also further away from that comfort thermostat set point. If we look at the daily, the hourly fluctuations, it becomes even more prominent. And we thought something like this, a real world record would be a lot more useful and representative, because condensation would be more manifested in those extremities than we would with the averages that you find on the RMY. So the first step was to really convert BOM data as we downloaded them into a format that was able to be read by Chinoth engine. And the next step was to work out an engine that could do the simulation found in ISO 13788. Here is an example of a brick veneer construction together with all the R values and the vapor permeability values. So all this was put into the software so that we could run the simulation to see whether we were coming out with the same answers as was simulated, as recommended by ISO 13788. And once we could run this simulation, it was really a matter of time to do it in a way that we could loop it to be an hourly thing. So here we see a snapshot On top is the dew point diagram that shows you the thickness of various construction materials and whereabouts we'll find temperature dropping below the dew point. When temperature drops below dew point, that is where condensation happens. The dew point analysis tells us where it will happen. It doesn't tell us how much happens, and that's where the Glaser method comes in the step below, which quantifies the amount of condensation or evaporation that happens on each surface. Now, the ISO 13788 has a monthly method how we go about averaging temperatures over the month, which in this case we decided that we would substitute with an hourly method since it was all available from the G-Earth engine. So when we put this together, we will get this kind of a simulation that takes us hour by hour and basically shows us where condensation happens and how much of it is going to be happening. We thought we could do a bit better by showing a bit of the history behind, so that each time we looked at it, there was basically lines below that show the past 24 hours where condensation was happening. We would show a green polygon. Where evaporation was happening, we would show orange dotted lines. And that was helpful to just see snapshots, but I think what we found really useful would be if we could take that and see how that overlaid with the risk of mold growth. So here is another representation of basically the same study, but now we're taking, instead of a snapshot, we're taking the whole year's worth of 8,760 hours. And what we're doing is that we're creating a threshold. In this case, we're just picking an arbitrary threshold of 48 hours of persistent dampness. Where that happens, we'll put a blue line through to mark that there is the risk that there's enough condensation for mold to actually grow. So what we see in the graph below, which is a snapshot of the first point where that threshold was breached, is the gray plots that shows you the condensation and evaporation. Where it evaporates and it is all dried out, the red shows you the cumulative effect. So it's a cumulative effect of all evaporation and condensation until such point as it is completely dried out, so that we can see its length, whether that exceeds 48 hours, and what the patterns were like. So this is looking at one building, and the next step we wanted to do was to look at how we could introduce soil air temperatures into the mix, and we found that there was no soil air temperature difference between the east and the west. And when we investigated into the climate files a bit more closely, we found that this particular climate file had a perfect symmetry between the morning and afternoon, which was very different from the Bureau of Meteorology record found below. And that was another reason for us to feel that it was much more important for us to look at a BOM record than to use the embedded files if we wanted to do an hourly kind of condensation risk analysis. So after we had fixed the climate inputs, this is what it looks like looking at the south. In this case, during the winter in the south, there is very little soil air temperature as a result of direct solar, but there is a contribution as a result of the diffuse solar. And so this is the south side that shows that it's not doing very well. There are many points at which we find there is condensation happening. For the north, we find a completely different picture. There is no single period of 48 hours throughout the whole year where there is persistent dampness. So condensation does happen, but it always dries up within the time limit of 48 hours. And now this is on the east, and the next one will show you the one on the west. We find that the east is in a sense more problematic than the west. I'm showing you the west now. And looking at the climate files, we can see that the times where the temperatures are warmer, the air temperatures are warmer, are in the afternoon, and that coincides with the time also of the sun being on that western wall. And as a result, there was a greater drying potential, and you had less instances where moisture persisted in that western wall. So very briefly, this is a summary of that case. This is the house that was used for that analysis, and it is used for the software accreditation protocol. So as a proof of concept, we found that we could show the top graph showing what a wall would be like in terms of it being in full shade with no direct and diffuse solar, or facing the south, east, west, or north walls. The time to run the simulations is not altogether quick, and if you want to do an hourly simulation, it takes about 32 seconds thereabout on a laptop. So I think whilst we have a proof of concept, there is much more we can do to optimize the software. But in the meantime, we were satisfied that as a way of flagging out potential problems with certain walls, it was a way that did not require additional modeling input, in the sense that if an energy assessor already modeled the building, they could run this simulation as the step subsequent to running the mandatory simulation for coming out with a star rating to get a certificate anyway. Much of this inspiration comes from this book, The Cathedral and the Bazaar, musing on Linux and other open source software. And I think the motivation behind this is to make an open source software so that other building scientists who have interest would be able to make contributions. And I think the part that I like to take from this one is particularly point 8. Given a large enough beta testers and co-developers, every problem will be categorized quickly and the fix obvious to someone. So on that basis, I would like to welcome any other building scientists who have an interest in condensation analysis to join us. So that's me, Tim Law, and Dong Chen. Thank you very much.